So here we study regular curves and arc length. Okay, so topics: regular curves and arc length. Okay, so let us start with a parameterized differentiable curve alpha from a comma b interval a comma b to Rn. Okay, so suppose this is interval a comma b, and suppose this is curve. So this is the trace of trace of alpha. Let t naught be a point in the domain. Let t naught belongs to a comma open interval a comma b, and here is the corresponding point alpha t naught. Then alpha, so suppose alpha prime at t naught is not equal to 0. So what is alpha prime t naught? This is equal to alpha 1 prime t naught and so on alpha n prime of t naught. So suppose the tangent vector, so this is called tangent vector of the curve at the time t naught. So the straight line defined by so t sub t naught, this is from R to Rn. So parameterized straight line given by t of t naught at x, this is equal to alpha at t naught plus x times alpha prime t naught. So this is parameterized straight line. Straight line. So here what is the parameter here? Parameter is x. So what is this? This is the tangent line of the curve alpha at alpha t naught, at the point alpha t naught, and this is called tangent vector. Well, and the trace of t sub t naught, this is the line. So this is the line, this is tangent. Okay. Now we note that to study we note that to study the differential geometry of curves, uh, the differential geometry of curves, it is essential that so first of all tangent vector exists and it is non-zero. Okay, so it is essential that uh, it is essential that the existence of tangent line, and at every point existence of tangent line at every point. Okay, so when it exists, if this is not equal to 0, if so we define singular point where the tangent vector is 0, those points are called singular points. So definition: let alpha is a parameterized curve from a comma b to Rn be a parameterized differentiable curve. So a point T belongs to that domain. Domain is a open interval a comma b is called singular point of alpha if alpha prime at the point T this is equal to 0. Okay, and such curves are called bad curves. So we prefer curves with no singular point. So we prefer curves with without singular points. So such a curve is called a regular curve. So definition: alpha, if this is parameterized differentiable curve, alpha from open interval a comma b to Rn is called regular if it has no singular point, that is alpha prime of t not equal to 0 for all t belongs to the domain of open interval a comma b. Okay, so this is the definition of regular curves. Now we study arc length. So let us consider the curve. So this is open interval a comma b and this is the curve. Okay, so let us consider some interior point here. So t naught, so here it is alpha t naught. Okay, so alpha is curved from a comma b to Rn. So the function is defined on the same domain a comma b to So this is real valued is defined by s of t. This is equal to integration, so over t naught to t of alpha prime of u. So norm of this with respect to d. Okay, so this is called, this is, so this function defined by this is called the arc length function, the arc length, so arc length function, and this is based at t naught. So for example, if t is here, then alpha t is here. So s of t, this is the length of the segment of the curve alpha from alpha t naught to alpha t. So length of this portion is equal to s of t. So this is called arc length function based at t naught. So well, we consider an example. Consider gamma t. This is equal to e power t cos t comma e power t sin t. So spiral. Then what is tangent vector? Tangent vector is following the derivative of gamma with respect to t. This is equal to e power t cos t minus e power t sin t comma e power t sin t plus e power t cos t, and this implies norm of gamma prime of t. This is equal to well, let us compute e power t. So norm square, this is equal to e power 2t times times cos t minus sin t square, cos t minus sin t square plus cos t plus sin t square. Okay, and this implies norm of gamma prime of t square. This is equal to e power 2t times her. Okay, so 2 times cos square t plus sin square t, and this is equal to 2 e power 2t. So this implies gamma prime of t has norm equal to root 2 times e power t. So we have so this is page 1. This is page 2. This is page 3. So let us go to the next page, page 4. So now we compute the arc length function s of t this is equal to let us consider the base point as 0 to t, norm of gamma prime of u du, this is equal to 0 to t root 2 times e power u du, and this is equal to uh, root 2 times e power t minus e power 0, that is equal to 1. So this is the arc length function for the curve gamma t equal to e power t cos t comma e power t sin t. Okay, and here we have remark. So our remark is uh, as per the definition, St is always differentiable, and what is the derivative of St, and ds dt equal to, by the fundamental theorem of calculus, and this is equal to gamma prime of t, norm of gamma prime of t. Okay, so where St equal to t naught t gamma prime of t, gamma prime of, yeah, this is u and du. Fine. So now we have some more definitions. So definitions. So first we let gamma is differentiable, parameterized differentiable curve from a comma b to Rn, parameterized differentiable curve. Then the speed of gamma at the point at t, at the time t, is norm of gamma prime of t. Second, if the length of gamma prime t, that is if the speed of gamma at every t equal to 1 for all t in the domain, then gamma is called unit speed curve. Unit speed curve. And third one, if gamma is unit speed curve, that is norm of gamma prime t equal to 1 for all t in the domain a comma b, then what is the arc length function? Arc length function based at t is s of t, this is equal to t minus t naught. Okay, so and such a curve gamma is called parameterized by arc length. Parameterized by arc length. So we note that for simplicity we restrict our curves parameterized by arc length. So we prefer the curves are parameterized by arc length. For simplicity, we restrict our curves parameterized by arc length. So next time we study reparameterization. So there we will show that every regular curve can be reparameterized by arc length. So we stop here.